So welcome everybody. Most of you should know Violeta. She arrived a year ago from Zaragoza, and she has been working with some models of biological dynamics. There's supervision of Sandro Meloni, and she will now, in the context of the presentations that all the students should do of the ABU for the PhD, she will present the results of the first year of working in spatial static interactions in competitive ecosystems and collaboration with Sandro, but also with professor at the University of Zaragoza in social economics. So, please.
Okay, thank you, Emilio, for the introduction. Yes, so let's start by saying that in nature we find a wide variety of ecosystems that have a lot of species living together. They are coexisting together. So it's normal that the problem of coexistence has become important in ecology. They try to study what are the mechanisms, the important mechanisms that affect coexistence. And more precisely, we have a little problem when we take competitive interactions into account, because previous results, previous hypotheses, like the competitive exclusion principle, tell us that when we have a species competing in an ecosystem for the same set of resources, for example, in a forest, plants competing for, as every plant needs, from nitrogen, phosphorus, water and sun, the exclusion principle tells us that only one species will survive. But of course, this is something that we do not find in nature. And moreover, we want that coexistence to be stable. That means that if the densities of the species that live in that ecosystem are fluctuating through time, it might be probable that at some point one species go extinct. Or moreover, in that situation, if the system is perturbed, it will not be able to recover from that perturbation and recover its previous state. We prefer the densities to be in their equilibrium point. And in the past decades, it has been a lot of theories that propose mechanisms to study ecosystems. For example, random matrix theory. Well, in fact, it predicts that there will be no coexistence for large ecosystems. Also, Newton is theories, and more recently, the introduction of higher order interactions. Apart from those possible theories, there is also space, and we will focus in space, in how the space and in the interplay between the space and the emergence of a stable coexistence of species. So we will study competitive interaction with the space, what we call a structured interaction, that are the competitive interaction that arise because of the location of the individuals in the space. And then I will compare the results with the higher order interaction model. So to sum up, firstly, just in order to be able to compare both models, I will introduce what are higher order interactions. Then I will explain our model for structured interactions. First, we will explain how we will encode the space and the dynamic we simulate in these systems, our results about coexistence and stability, and then the comparison. So, well, let's start by saying what are not higher order interactions. Typically, we think about just two species, so pairwise interactions, and those two species are competing. And there are some models that say that in that situation, it might be a coexistence of all or several species, but the evolution of the densities of those species through time heavily fluctuates, and it is not stable. The dynamic is in a limit cycle, and it's not stable. Now, so far we have just taken 2 species into account, and higher order interactions means that now the outcome of the competition among those 2 species will also depend on the presence on a third, 4, 5 species. And in that situation, the system has been seen to converge toward its equilibrium and become stable. So far, higher order interactions, now structure interactions. As we want to study the influence of the space in the dynamic of our ecosystems, we need a system to encode that space. And we will use 2 main key ingredients. One is the spatial arrangements of the individual in the ecosystem, and the other one is the interaction range. That is how far or near need to be 2 individuals in order to be able to compete. And those 2 ingredients will finally define what we call the competitive structure interactions. So we have chosen 3 kind of networks that symbolize our spatial arrangements. We go from the random typical order ranging graph, where actually there is, of course, no spatial structure, to a square lattice, where that is a higher structure ecosystem. Nodes are placed homogeneously in fixed positions. So these are then I will explain later the random geometry graph, don't worry. So these are the graphs that we have chosen to represent the location of the individuals, and they will also tell us how they interact. For example, this is the lattice. So in our model, the individuals live in a node, just one individual per node. And here they are arranged accordingly to the square lattice, and how they are going to interact. Well, if the interaction range is very, very short, they will just compete between the nearest neighbors. In this case, the purple with those 4 nodes. Now, if we increase the range of interaction, we increase the number of neighbors our plan is able to compete with, and they will be the neighbors of our neighbors. That is, those nodes. So, choosing certain spatial arrangement plus certain interaction radius will configure a certain network topology. The same is true for the random geometric graph. In this case, the coordinates of the nodes are chosen randomly in our ecosystem, and they will interact according to an interaction radius. So, for example, again, the purple individual now has this interaction radius, so the competitions will occur in this through 3 individuals. Here we have the links. Increasing the interaction range leads to bigger neighborhoods, a higher degree for the purple node. Now that we have said how we encode space, let's focus on the dynamics. As we wanted to study, to explore how space influences in the dynamic of the ecosystem, we have just kept to the minimum the number of ecological processes. So we do not have migration, neither emigration of species. We just have an isolated community of n individuals that with n as species. In this case, three species, because it's more simple. This is the network corresponding to the previous random geometric graph with a short range. And what are the ecological processes that we will take into account? Well, a death process. So one randomly, one at a time step, one plant is chosen to die. And now the competition arises among its neighborhood. The competition will be to fill this vacant node with an individual of your same species. How is going to be this competition? Well, firstly, pairways, because we want to compare our model, which is spatial, with a higher order model. So let's keep things simple and just study pairways competition. And then the dominance among the species will be defined the same way as in the higher order models. So we can compare them properly. We have this H matrix that encodes the dominance and whose entries, HIG, is the probability of a species Y, winning species J. And in order to reach a coexistence, mathematically and ecologically, we need to have intransitive cycles. That is a rock, paper, scissors game. So blue usually wins purple. Purple. Then purple usually wins orange. And finally, orange usually wins blue. So, like the paper, rock, scissors game. And when in that case, finally, the purple wins. And with that dynamic, we obtain several dynamical responses. We can have a dynamics very similar to those of pairways interaction with heavily fluctuating densities, to another behavior where the densities are in their equilibrium points. Yes.
How do you choose the two individuals that are fighting?
Oh yes, sorry. Yes, good point. The interactions must be pairways. So among the neighborhood, we choose two at random. So we just suppose that only the seeds of the purple and the orange are able to reach the vacant node. Yes, thank you. Okay, so we want now to characterize the different behaviors we find. How we are going to do so? Well, keep in mind that every time step we have a density for every species. So we can imagine that the densities every time step define a point in a space whose dimensions are the number of individuals we have. Yes?
And the total number of species is constant? Or?
Yes.
So every time one dies, immediately you replace?
Yeah. Yes. Every time during the simulation, all nodes are occupied by an individual. Yes.
The number of species and the number of individuals is constant, both.
Yes, both.
The number of species could be patient.
Yeah,
no?
sure.
Yes.
Only decay.
Yes, only go extinct. Yes, but no new species are introduced. So as the number of species is constant, and as time evolves, this point will move on a simplex that lives in a plane in the space. And here, for example, the corresponding path of the point is a cycle. So we will measure the area that encloses this cycle as a parameter of the behavior of the system. So here we have the area in the simplex, and now we want to connect that behavior, that area, with our spatial parameters. So we will have the two ones, one the interaction range, that in this case is encoded in the mean degree, because a higher interaction range leads to higher neighborhood. Like, of course, the nodes that live there have higher mean degree, and on the other hand, if we decrease the interaction range, we will have a smaller degree. And then the other ingredient is the spatial distribution of the individuals. So we will have one curve for every kind of graph. We start with the mean field approach. That is when we choose the two competing individuals for the vacant node, not in the neighborhood, but just with a probability that is proportional. Well, that is the density of the species in that moment. And we will obtain. We have obtained high area in the simplest, those kind of dynamics. And now the same behavior, that is very big areas, are also obtained when we simulate or model in an ever-ranging graph. But in that case, the behavior is obtained regardless of the range of interactions. So for big neighborhood and for little neighborhood, we obtain the same big fluctuations. And now, if we introduce a structure in our, yes, Javi?
But sorry, is this at one realization or?
No, it's the average over
Okay.
lot of realizations, and the shades indicate the maximum value obtained.
Okay.
Yes.
Several realizations with different realizations of the network, not several realizations on the same network.
Yes, exactly, with the same P. In the case of the Interdisciplinar graph, it must have the same probability. And now we obtain a different behavior with our two structured networks, the lattice and the ever-ranging graph. Here, this is lattice, and this is the random geometric graph. Sorry. So we have a region of long-range interactions where the areas, that is, the fluctuations, are big, but as we decrease the interaction radius, we arrive at a regime that corresponds to do those kind of dynamics where the area decreases a lot. So adding the structure network and tuning the range of the interaction permit us to arrive to those kind of dynamics. So now, pause. So far, we have seen that we can obtain coexistence of species with those two ingredients, and now we need to see if that coexistence is stable or not. And in order to do so, as this is an agent-based model, the simplest way is to perturb the system and see what happens. So at third time, we have a perturbation, and in this case, it's a pulse perturbation, which means that at some points, instantaneously, the density of, in this case, the blue species reach the 80% of the population suddenly. And we want to see how the system recovers from that perturbation. This is an thumb of this part, and here I have just plotted the blue species, and we see that even for a big perturbation, the system, the perturbation exponentially decays, and finally we again return to the previous behavior. So we can say that the system is stable. Yes.
So, sorry, you were checking that the limit cycle is stable from outside, right?
No, not the limit cycle. I mean, we are not interested in those dynamics because as the fluctuations are very big and are unstable, because some perturbation any perturbation basically can lead to extinctions. We want to see if in this case the stability holds. And perturbating the system, we have seen that that is stable. So why we have studied just this? Because we wanted to compare our result with the higher order model. Because when in the models where higher order interactions are added, we can go from a situation of heavy fluctuating densities to a situation of convergence, and a stable situation. How? Just adding the higher order interactions. And we have obtained the same result, but not with higher order interaction, but tuning the range of the interaction. So if we have a network with a structured spatial arrangement, and we set the interaction to a short range, we also obtain a regime of a stable coexistence. However, if there is no structure, regardless of the range of interactions, heavy fluctuations, and if there is a structure, but the range of the interaction is very big, we also have heavy fluctuations and no stability. Yes, Rodrigo?
Yeah. But actually,
Yes.
when you are checking that it's stable, you are checking the conditions for a spike in the density of the population. But if you have lower density of population, what will happen?
Well, actually, increasing
still stable?
one species a lot is the same as decreasing other species a lot, because the number of individuals is constant.
Okay.
So if suddenly I put the occupancy of the community an 80% of blue, then the other two species must divide between itself the other 20%.
So you're checking that it's stable when you always increase one of the species only.
Yes.
So what happens if you increase the population of two species and decrease the population of one?
No, but
I mean,
well,
if it's still stable, the whole space.
yes, but I mean, as the number of individuals is constant, that perturbation wouldn't be that extreme, because what do you propose? 30,
if you go from
30
another
plus.
direction in phase space, I don't know if it's still stable or not.
Sorry, could you repeat?
If you go from another direction, from phase space, I don't know if it is stable, still stable or not.
Yeah, but what I'm trying to say to you is that if you increase, you cannot increase a lot to a species, because the densities must sum 1. So, yeah, we can also check putting 40, 40, and 20 or something like that. Yes, but during this this dynamic, at some point you have those densities and the system evolves correctly. Yes.
Yeah,
we will just
then
need
you
to
would
check if
change
in
the
this
dynamics from
in this
stable
dynamic.
to oscillations. I mean, okay, later we can.
Okay. Well, now that we have the main result, I will just say that, okay, here in the higher order interactions, the convergence, the integration of the ordinary differential equations give us a smooth convergence to the equilibrium. But here in our computer simulations, the convergence is not that clear. So we have studied what are these little fluctuations, if it is noise or it is something else. So in order to check that, we have checked the scaling of the fluctuation size with the system size, that the system size is just the number of individuals of our community. And the fluctuation size is the variance of these areas of these densities. So
the standard deviation.
The standard deviation divided by the mean of the density. So as we see, the fluctuation side scales with the inverse of the square root of the system side. This is an exponent close to minus 0.5. So that means that this might be just noise due to the finite side of the simulation. So now, just for just the conclusions, as I have just said some slides ago, the main result is that we can tune our system and go from an unstable coexistent state to an stable coexistence is if the network, if the spatial arrangement of the individuals, if it is a spatial arrangement of the individuals, that is a spatially structured network, and the interaction among plants are small. But if we increase the range of interactions, we lose that stability. And we have also checked that in ecosystems where there is no spatial structure at all, we also obtain just unstable coexistence. And this is analogous to adding a higher order interaction in our system. So now if you have more questions, I will try to answer them. Thank you.
More questions?
Yes.
So as the model is pretty simple, no? Have you tried to do some theoretical stuff or something?
Yeah, we have tried, but well, the main result is that as having source range and spatially structured network means that there are a lot of spatial correlation. It is very difficult to propose some equations without any strong assumption, because the typical assumptions get rid of the spatial correlation. So the results that we have obtained with those equations are not useful for the model. Yeah.
Just because to add something, the simplest approximation is the mean field approximation.
Yeah.
And it includes always the lower behavior, which is not what happens for sure. And the next approximation will be some better approximation, something like that. I don't know very well. I don't remember the name. Nagy did the questions and they don't reproduce that. Someone has to be questions.
Yeah, the questions are welcome.
I have another question. You talk about stable coexistence and unstable coexistence, but I mean, that's a limit cycle actually is a stable coexistence. My own name.
In the higher order interaction model, the paper that I have put in the reference previously of like Riley and Alcina, it's been demonstrated that that limit cycle is not stable. So maybe instead of limit cycle, it should be called that they are just neutrally cycling or something like that. Yeah.
It's not stable, where does the system goes?
No, I mean if this is perturbed, just one species will survive. So.
Okay, and the final state is not a thing, that's only transient.
No, I mean if the system is not perturbed and it's integrated over time, in this situation, it goes forever. But if something strange happens, then only one species becomes hegemonic.
Yeah, just in the biological literature, they use this stable and unstable when they are stable when it fluctuates unstable. This is not what we like, but they don't like this nomenclature, but it's used. And what she says is that even in the dynamical systems point of view, some mean field models that we have equations, you can check stability or unstability. In some of the mean field models, the limit cycles are not even stable, but marginally stable, which means that but anyway, this is a particular model. In general, there will be limit cycles.
Okay.
And there will be stables in the dynamical systems nomenclature, but when something fluctuates very heavily, it's called unstable.
Yeah, I have just defined what stability means at the beginning because it's
and then I have another question which is difficult maybe because but if people that study dynamical systems see one thing which is stable fixed point, and then you see limit cycle, then you would expect a whole bifurcation somewhere.
Yes.
And for that you need to change the perimeter continuously, probably I don't know that you have that in here.
No, here no. It's an individual based model. So.
Yeah, but still, for instance, we are changing some things there, no? So that maybe you could change continuously, going from short range to long range. That's something that you can do continuously, no? Oh, actually, you showed the long this one.
Yeah, this one.
Yeah, so that's an imperfect code probably because of noise, no? So that's even some.
Yeah. Yeah, well, we have not seen it.
I have a simple question. Do you measure the area of the simplex to give some sort of how stable is your system? But do you measure the location of the cycles also, if they change when you change R?
And
like the location of the cycle, measure the area, but yeah.
What do you mean, the location? I mean, every cycle is orbiting around the mean density, around a mean density that happens to be the equilibrium density.
But when you change R, this equilibrium density changes also?
No.
No, okay.
No. It's robust.
Yes, I missed some point because the model is stochastic, right? So that's
The probability of winning is a probability.
okay. So at some point there is like non-zero probability to touch the one absorbing state. So at one point you will always end up in the situation of just having one species, right? Like this is a pseudo-stationary. When you say that you have coexistence, you have coexistence on a long time, let's say, not like scales with
On a really, really long time.
Okay. So, but when you have these possibilities of the population fluctuating or the really stable state, let's say, is it more robust in this sense of because there you have the densities of one of the species that are fluctuating. So I would expect that it's more like probable that one of these species will touch that certain state.
So if I have understood you correctly, yes, in these situations, rare heavy fluctuations may occur. For example, here, maybe the blue species would have died perfectly.
Okay.
Yes, this is probable. That's why we will just focus on the smooth, on the short range dynamic, because the long dynamic, is very probable.
Yeah, sure. Okay, thank you.
Just a point is that what can disappear is can decrease by fluctuation is the number of species, but the number of individuals by fluctuation is also
sure.
But someone by fluctuations may decrease, and if in the tail of times it will decrease. Any more question? If not,